So, welcome back students. In the last lecture basically we were discussing redundant functional group based strategies, and we said that redundant functional group plays a very important role and is acting as a surplus functional group. In the target molecule basically you do not have that functional group which is required, but still in some cases we say that you need to introduce some functional group which act as a redundant functionality, and you have to remove those functional group to bring a inert functional group like hydrocarbon. Hydrocarbon does not have active functional group. So, you need to introduce some alcohol or some carbonyl group, and the late stage you do the deoxygenation or alcohol removal to introduce the hydrocarbon functionality. So, our next problem will be based on a similar kind of exploration of redundant functionality, and this problem was very nice demonstration of redundant functionality. Here we have given you a target molecule which is purely a hydrocarbon. It is basically a tetra substituted cyclopentane. There are 2 methyl groups, there are 2 ethyl groups, 1,2 ethyl, 1,3 methyl, and all the groups the relative stereochemistry was above the plane. These 2 are ethyl group. Eventually the starting material was also given to you. The target molecule is this. The starting material was a very simple starting material, cyclopentadiene was given to you. And normally I can give you a hint that whenever a starting material cyclopentadiene was given to you, blindly you can think about this instructor or your teacher is looking for a Diels cellular cycloaddition reaction, because cyclopentadiene is a very good diene, a 4 pi system in the Diels cellular cycloaddition reaction. Now, Diels cellular transformation you have to use it, but before that let us go for the retro and how the concept of redundant functionality you can introduce or you can bring it here. We say that probably if you have something like this, all the things are CH2Br, CH2Br. So, basically we are trying to have a tetra bromo compound. So, this bromo compound can selectively reduced by a hydride source to corresponding hydrocarbon. This you already discussed, or if you not discussed, just remember that if you use a alkyl bromide or alkyl halide react with lithium aluminum hydride, eventually you can get the corresponding hydrocarbon. Also you can use a radical mediated reaction if you use Bu3SNH and AIBN, that also is quite possible. We will explain this reaction little bit later on, but first remember any hydride source will be working here to give you the hydrocarbon. So, this is basically FGI. Okay. The point is you have to introduce 4 different functional groups here. Our next retro was similar kind of FGI, where you say that if you having a tetraaldehyde kind of thing, tetraaldehyde, this tetraaldehyde basically can be reduced to give you the tetrol, which can be converted to the corresponding tetrabromide. So, this is also FGI. And now we will be doing a very interesting retro. Now, this retro is very interesting. The retro which now will be doing, it is very interesting. Both the hydrogens are below the plane. So, if you closely follow this compound, this is basically a bicyclic compound. Now, we say you will be simply doing a ozonolysis here, means that you will be chopping this double bond here, you will be chopping this double bond here. So, basically the core cyclopentane, which is this, the core cyclopentane will be retained, and then you are having CH2CHO by ozonolysis, CH2CHO, 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 and this part you will be having another CHO, another CHO. So, this is absolutely fine. Next I say, as you have already told that you have to use a Diels-Cellular reaction because starting material was given a cyclopentadiene. Our next retro will be based on a exploration of redundant functionality. I will say that if you have this kind of compound, you basically deoxygenate both the carbonyl oxygen and you can think of having this kind of retro. This is basically that concept of redundant FG, and then here is Diels-Cellular retro. So, you can basically now write a 4 pi system and a 2 pi system as your parabenzoquinone as the dienophile of the dienophile. So, now based on this we will be now doing the forward pathway and we will see how this synthesis can efficiently be carried out with a strategic exploration of redundant functionality. The starting material was cyclopentadiene and was reacted with parabenzoquinone. Okay. So, initial 4 plus 2 cycloaddition, you basically normally we know the 4 plus 2 cycloaddition, the endo product was usually formed. Endo means this is the this product. Okay. Now, as you said, this 2 carbonyl was not required. So, need to get rid of this 2 carbonyl. And if you try to remember, you can do variety of reaction, but the reaction which we will be doing will just protect this carbonyl with 1,3-dithiene means SH. So, what we will get? We will basically get the corresponding carbonyl will be protected as its thioacetal. Okay. Now, as both the carbonyl has to be deoxygenated, here we will be doing the Mozingo type reduction which you have already explained, means you need a renin-nickel. So, after this Mozingo type reduction, your this part is now this. So, basically you are now coming to this compound which is ready for the ozonolysis, is not it? So, now do the ozonolysis, and if you do the ozonolysis now, I will write the compound in a different way. I will write it double bond O, okay. Then this the core cyclopentane, and from here you basically getting one aldehyde and getting one aldehyde, and this compound is basically nothing. You can just simply write that this compound is your CH2 CHO, CH2 CHO, and this is your CHO, this is your CHO. The stereochemistry you can basically write it out, or for simplicity, simplifying the things, you can omit the stereochemistry. Now, next what you need to do, all the aldehydes need to convert it to the corresponding primary alcohol. So, do it by a sodium borohydride type of reducing agent, all are converted to the corresponding primary alcohol. Then you do a Appel reaction, Appel transformation by TPP, triphenyl phosphine, and CBr4. So, basically then you will get tetrabromo species, this Br, tetrabromo. Now, once you have this tetrabromo, your next job is very much similar. Next job is pretty simple, and the next job basically we say that you have to now remove this bromo with hydrogen to achieve the target molecule. So, basically need a dehalogenation reaction, and in principle you can do this reaction by varieties of way. I will just explain. If you can take this compound, use lithium aluminum hydride, you can end up with this desired product. Okay. So, this is the target molecule. Otherwise, there are other ways you can also do it. This particular reaction will be explaining little bit later on. If you have Bu3SNH and AIBN, a radical pathway will operate. I will explain this radical pathway little bit later on, where when you explain a name reaction, which basically is very important in the context of redundant functionality. So, if you analyze the entire problem, you will find that we explored the strategy of redundant functionality twice in the synthetic pathway. Initially, we do a Mozingo type of reduction, at this point you basically get rid of this this 1,3-dithione moiety to deoxygenate this carbonyl, and then when you have this bromo, you do another kind of redundant functionality exploration by using hydride source. Now, next based on the redundant functionality, we will be explaining a name reaction which is now very popular. The name reaction is named as Barton-McCombie deoxygenation or Barton-McCombie reaction. Now, in Barton-McCombie reaction, the basic retrosynthetic pathway you can explain in something this way. If you have to make a hydrocarbon molecule, you just take the corresponding hydroxy and then do this Barton-McCombie reaction to access the hydrocarbon. It is basically a deoxygenation reaction. It is a deoxygenation reaction. This is very helpful reaction, and Barton-McCombie reaction was used quite often. Now, in the Barton-McCombie reaction, what is the main rule of different thing? So, you will find that if you have a alcohol, you first react with carbon disulfide and then you react with a methyl iodide. So, basically you get a this kind of xanthate ester. Now, this xanthate ester was basically then subjected to your radical fragmentation. And this radical fragmentation, normally we use, as I said, two reagent AIBN, which is aja isobutyryl or nitrile, whose structure is isobutyro. So, MECN, then this is having aja, and then the remaining part MECN, and you are having Bu3SNH, whose structure is normal butyl whole 3 SNH. Now, initially if you shine light to this molecule, the nitrogen bond basically initially opens up and nitrogen gas was evolved, and then you get this radical through a heterolytic cleavage. You get this radical this basically this and this, you get this radical. Now, this radical what it does? It basically picks up the hydrogen from the BU3 SNH. It basically picks up the hydrogen from BU3 SNH and gives you BU3 SN dot. Now, this BU3 SN dot, this particular BU3 SN dot is now reacting with the xanthate. So, you have this xanthate in your reaction mixture, or is a this xanthate you basically initially prepare, is not it. Now, this BU3 SN dot, this BU3 SN dot is basically reacting with this sulfur, reacting with the sulfur through a half arrow. This is a radical. So, you will be always having this kind of half arrow mechanism, and this is also like this, and then you will find this compound will be then converted to a ROC S Me S SN BU3. Now, this kind of things will be basically now putting a radical here. Now, this radical will now having a carbon oxygen. So, this heterolytic cleavage will now takes place, and you basically having this and this cleavage. So, which will now give a this oxygen bond cleavage is give you a R dot, this particular R dot. So, these things and sorry, this will be like this. So, you have this R dot and your entire other things will be chopped it here. So, basically you get this R dot. Now, this R dot will get a BU3 SNH which is in the reaction mixture, and then it will pick up the hydrogen from this BU3 SN, it will give you a hydrocarbon which is required, and you get BU3 SN dot. So, BU3 SN dot is regenerated. Now, once this is regenerated, it can again abstract, or you can undergo radical fragmentation to this xanthate again. So, this way the whole process basically goes on, and then you will find that finally your hydrocarbon or deoxygenation was taking place. So, in a similar way, as I said, if you are having a alkyl bromide, you can basically react with AIBN and BU3 SNH. You can also get a similar kind of carbon bromine bond heterolytic cleavage. You can get a dot radical, and then it abstracts a hydrogen from this BU3 SNH to give you a RH. So, this kind of radical mediated deoxygenation, particularly this Barton-McCombie reaction, was one of the very well known reaction, and it was explored in the synthetic organic chemistry for many long time, and for many years. So, eventually for the redundant functionality, you can basically now make a note of summary that what are the transformation we are normally using in the redundant functionality, redundant FG. Now, you can see the transformations are basically the reaction where a functional group has been removed. Standard transformation like Wolff-Kishner reduction, where basically doing a transformation something like this to deoxygenate the product. The same line you have this Clemenson reduction, this is also exactly same. We said Mozingo type of reduction, Mozingo reduction, which is also very useful. Now, what is the exact reaction? you basically have to have a sulfur compound and then you do the desulfurization reaction with Raney nickel, and then what you get? You get the corresponding hydrocarbon, and then finally we called a name reaction which is Barton-McCombie reaction, and you say that in Barton-McCombie reaction the transformation is you first convert a corresponding alcohol to the xanthate ester and then you shine light with Bu3SNH and AIBN, then basically you get the corresponding hydrocarbon. So, these three are the main key reaction, in this radical mediated or this kind of exploration of redundant functionality, where you can get rid of a particular functional group to convert corresponding deoxygenated things, and this three transformation was often used if you want to explore the redundant functionality. The other functional group transformation which we just now said is basically extension of these things, like if you are having a Rx, now X could be anything, X could be chloro, bromo, iodo, tosylate, mesylate. This case also this carbon heteroatom bond cleavage you can do by different way. I said there are ways to do it. If you can use a hydride donor which can act as basically a nucleophile, and you can also cleave it by radical way. Now, radical way is which you just explained, Bu3SNH and AIBN, and if you need the hydride donor you take the corresponding Rx and react with a series of hydride donor like lithium aluminum hydride, strong hydride donor mainly. Sodium borohydride sometimes works, but lithium aluminum hydride is very reactive sometimes. Superhydride LiET3BH works very well, So, this particular hydrides and X could be anything, I mean any halogens, mainly if you are having a good leaving group like iodo and tosylate, the reaction is very faster, and you will always get the corresponding hydrocarbon in very good yield. So, in principle this kind of sometimes I can give you a very similar kind of example, but in principle you may not call it as a redundant functionality. I say you are having a amide and you want to convert this amide to amine. Now, basically what you do a deoxygenation reaction, but in reality this is amide carbonyl, you cannot do a Wolff-Kishner or Clemenson kind of reduction. Okay. But already we have discussed it. Now, if you put a reducing agent like lithium aluminum hydride, so initially it was been known that the carbonyl reduction will takes place, and then instantly water elimination also takes place to give you a imine. Now, this imine particularly will now excess LH if you use, then the imine will be simply reduced, to give you the, this is basically imine will be simply reduced to give you the corresponding amine. This is probably all of us know it, but this is the imine and it goes through this way. Now, in true sense this may not be a redundant functionality. Basically the functional group was there, though we are doing a deoxygenation reaction, still this particular carbonyl is such a different carbonyl, probably Wolff-Kishner Clemenson kind of reduction will not be operating here. Okay. And other things like Barton deoxygenation you cannot do it, because for Barton deoxygenation you have to convert this keto to corresponding alcohol. So, no need, if you just simply subject to this amide to corresponding reducing agent, instantly it will reduce to first imine, then imine will be further reduced to amine. So, it may not be expression of a redundant functionality, but this is a simple FGI, this is simple FGI, a simple FGI. So, there are ways which you can basically explore certain things, and particularly the concept of redundant functionality is a absolutely brilliant concept through which you can explore many synthetic pathways. You can explore many synthetic pathways. And always try to remember, let us give you some problem like this. I said you have to make this kind of hydrocarbon. It is basically trying to refresh your memory, exploration of redundant functionality. I say the starting material is, I will give it to you a cyclopentanone. So, how you can approach it? I say the target molecule is this one and starting material is this one. Now, eventually you see that the number of carbon, it's there are 5 carbons, there are 10 carbons here, 6, 7, 8, 9, 10. So, basically you need, now you do the conventional retro, and actually this kind of retro was done very initially, if you remember. So, if now try to get back to your old memories. If you are having some pinacol type of rearrangement, this pinacol rearrangement, which basically will give you this kind of spirocyclic ketone. This is the pinacol rearrangement will basically give you this, then this migration takes place, you come to here. Now, so this and this, the main thing is your redundant functionality. So, simple exploration of redundant functionality will basically lead you to the target molecule, as I said. Now, here also you can, so what are the reaction you will be doing here? You can do a simple all the Wolff-Kishner, your Clemensen, Mozingo, all this kind of deoxygenation you can use. You can simply reduce this compound to sodium borohydride to get the corresponding alcohol. You can then do the Barton-McCombie, fine, Barton-McCombie, or even you can do it other way, you can reduce it sodium borohydride and then convert the alcohol to corresponding tosylate or bromo, and then you use the lithium aluminium hydride as your hydride source. So, in reality, no matter what are the reagents you are used, but eventually you have a much more flexibility to adapt a redundant functional group based strategies, and you see for this transformation you have numerous ways, and depending on the resources which are available in your lab, you can basically choose any one of the reagent system to get rid of this target. And the only thing is the power of the retrosynthesis is very useful. So, you have to formulate the proper retrosynthetic pathway, and the toolboxes, as we are discussing, there are toolboxes which are basically your retrosynthetic pathway and your transformation, your functional groups, your appendages, your stereochemical strategies. So, those knowledge basically serve your main guidelines, main toolbox. So, we will continue our discussion, and till then have a good time. We will see you in the next lecture.